In this video, I will present the concepts that are associated with Walker Chapter 8, that's potential energy and conservation of energy. So concepts, we have a lot of them, 2 pages worth. First one is gravitational potential energy. It's in joules. Energy is always in joules. Every type of energy and work, all in joules. So gravitational potential energy in joules, it increases with height and mass. So if I have a tennis ball and I want to increase its gravitational potential energy, I have to lift it up. Now it has more gravitational potential energy. When it comes down, it has less gravitational potential energy. Left and right doesn't matter. Another way to get more gravitational potential energy is not to use a tennis ball. If I use a bowling ball, at the same height, I have more gravitational potential energy because its mass is larger. Where is the gravitational potential energy equal to 0? Well, you get to choose your own 0 position. Just like in kinematics, we would choose whatever our 0 height was to make the problem as easy as possible. Do the same thing with gravitational potential energy. Often the best spot is the floor. So at the floor, the ball will have 0 gravitational potential energy. Above the floor, it has positive gravitational potential energy, and if it goes below the floor, then it would have negative. So this type of energy, unlike kinetic, can be positive, negative, or 0. We also have elastic or spring potential energy. That's the energy that's stored in a spring or other elastic material. So I have a spring here. Right now the spring is at its natural length. We can call this, so if I start here, we can say that this is the equilibrium position. If I move away from that equilibrium position, then I am giving the spring potential energy. At the 0 position, it has 0 energy stored. If you stretch it, you're giving it potential energy. If you compress it, you're also giving it potential energy. This is a bad example because this spring is designed not to be compressible. A more ideal spring is a shock in a car. So a shock absorber in a car is naturally in a position more like this. So it can be compressed or extended. That's what an ideal spring is like. So we have gravitational, spring, also thermal or heat energy. So heat energy is produced when other types of energy are lost. And in fact, in everything that you do, you will lose some of the energy to heat. It's often friction that is generating this thermal energy. Mechanical energy means kinetic energy plus either of these types of potential energy. So it's all the types of energy except for thermal that we've learned about are all types of mechanical energy. We also have the idea of conservative force. Gravitational force is an example of a conservative force because if I throw a ball up in the air, when the ball comes back into its original position, it has the same amount of energy as it had when it started. So that's an example of a conservative force. So gravity and spring. Non-conservative force, if you go on a closed path, so before my closed path was starting here, going up and coming back down. If I go on a closed path that involves friction, then total work done on that path is not 0. Because if I had to do something like I'm going to start here, oppose friction across the board to this spot, oppose friction back here, I had to do work against the friction here. I have to do more work against the friction to bring it back. So this is anytime you're sliding something across a floor. So that makes friction an example of a non-conservative force. Your muscles are the same way. If I hung a mass on a spring and let it bounce, it can bounce all day, right? If I instead am holding the mass and curling it, I can't go all day because my muscles don't produce a conservative force. If it did, I would use a force to bring it up and I'd be doing work, and then that work would get somehow stored back in my muscles again when it goes down. That's not how muscles work. So these non-conservative forces convert kinetic energy to thermal. Also, energy is always conserved. Total energy doesn't change for any closed system. So unless there is work being done on the system from outside, the energy inside that system can change form, but it cannot increase or decrease. We can use energy bar graphs to help show this. So if I have some object at an initial position, a second position, and a third position, and its kinetic energy is changing, so it's not moving, then it's moving, and then it's stopped again. If my gravitational potential energy, say I start high, and then now it's lower, and then at the end it's down at 0. Elastic potential energy, no spring, so those are all zeros. And then thermal energy, 0, 0, and then has some value. If you add up all of these types of energy in every column, they add to 10 every time. And you can show it in an energy bar graph by having bars with a height of 10. Initially, all gravitational potential energy. Then here, some gravitational, but mostly kinetic. And then at the end, it's all thermal. So that's a way of showing it in a bar graph form.